In this video, we're going to continue our discussion of error detection, and we're going to consider the cyclic redundancy check. It is different from the checksum. It does, in some sense, all of these error detection schemes have a similar idea of that you have data, you perform some kind of operation on it. You're thinking of the ones and zeros as numbers, then you can think of it as some mathematical operation, but it might just be some electronic operation, some logical operation. And you have the data, you perform this operation, you send the result of your operation in addition to the data. The receiver does the same, looks for the same answer, same operation, looks for the same answer, and see if there's agreement, then presumably the data came over. Cyclic redundancy, so that's how they're the same, that, there is the data, some operation, the check, and the sender and the receiver. The differences, one of the differences is going to be that the cyclic redundancy check is going to be done serially. So the data will be sent through an electronic system, sort of in a serial fashion, sort of bit by bit. Now, that's not something you would want to do if you had your data in parallel, but at the lowest level of transmission, that's how the data is being sent, sort of in serial bit by bit. So this is a process for the lowest level of transmission where the data is already sort of serialized. And it is a method that one can sort of have some changes in, make some choices in, and then hopefully, if there are a particular kind of burst error that one might be expecting, if one doesn't think the errors are random, but a certain kind of error occurs, then one can sort of take the choices one has within the cyclic redundancy check and make the choices. It's going to be positions of excluded ors. And you can make those choices that would be more likely to catch the errors you think more likely to occur. We're not going to get down to that level, but we're just saying that that level of engineering is possible. Okay. So we want some operation. Okay. So we're going to say that CRC is a bit like division. In some sense, it doesn't matter. It's some operation. But let's imagine it were like division. So you would take your data, think of it as some large number, and you would divide it up, divided by something, divided by something smaller. And then you would get some number and some remainder. And so then if I'm dividing by something with n bits, then my remainder, if I divided by n, then my remainder would be a number between 0 and n minus 1. It's not quite this, but it's something like this. And then, we're not doing quite regular division. Division is sort of harder than it needs to be, and I'm not sure it would catch the errors we want to catch, but there's some mathematical process. And then some kind of abstract mathy way. People sometimes think of it as division, but we're going to think about it as just some electronic logical operation. Okay. So let's not think about it as division. Let's think about it as electronics. So we have the data coming through serially. We're going to put it through what's known as a shift register. So a register is something that holds bits. A shift register is something that allows bits to move one step to the left or right. And then we're going to add to the shift, and the shift register just can be used to uh, transmit data or to convert it from parallel to serial or vice versa. But the if we add in these excluded ors, then it's changing ones and zeros. The excluded or will change ones and zeros. Hence, it's doing some calculation on our data. And then that sets us up for an error correction scheme. Do some operation, get an answer, have the receiver do the same, see if you get the same answer. Okay. So again, something that holds an individual bit is known as a flip-flop. Something that holds a sequence of bits is known as a register. If that register has the special ability to send all the bits either to the left or to the right, then that is known as a shift register. So here's just the shift registers. Sort of, you have and in this example, there are 6 bits being represented, and there's some bit coming in on one side, some bit going out on the other side, and all the bits, in this case, are moving 1 to the left. Okay. And shift registers come in multiplication. In fact, a simple shift operation can be thought of as either a multiplication by 2 or division by 2. It comes in when you add floating point numbers. If you're trying to you have to get the exponents of 2 floats you want to add to be the same, and you're going to have to shift your mantisses to sort of compensate for changing the exponents. If you have parallel data and you want to move it into serial, or if you have data coming in serial and you want to move it out in parallel, shift registers come in. And then when you're at that lowest level of transmitting data serially, you can add in this cyclic redundancy check. So you're not going to perform this unless you're already sort of doing the serial thing. All right. So again, we're going to play, if we are playing with 16-bit shift registers with some excluded ors placed in, then again, there would be a 16-bit answer. And if the problems were random, you would expect, again, this 99.9985% of the time you would catch the error, the same as the checksum. But in the CRC, you have the shift register. Shift register is a shift register, but we're going to sprinkle in some excluded ors, and we can position those excluded ors, and that will make it, the positioning of those excluded ors can make it more likely that we might detect certain kind of errors. So if we know a certain kind of error is more likely to occur, some kind of burst error more likely to occur than others, than just a pure at random error, then we can sort of engineer our CRC detector to be more likely to pick up the more likely error. Okay, so the data is going to be serialized. It's going to be coming in, moving through these shift registers one at a time, and you're doing that for transmission anyway. And again, I remind you that in the computer, after you get sort of outside of that main system of the processor and memory, if you're going over to even to the hard drive, the data is in serial. So it's not necessarily from one laptop to another or something like that. It can be moving to a device within your computer like a hard drive or a solid state drive. That data is usually passed in serial, and so it can be checked along at that time. All right. So here's our picture. We have some data coming in. So we have that on the right-hand side there and up, that upward pointing blue arrow. So we have some data coming in. And then we have those circles with the X's in it are the excluded ORs. And we have this shift register that is shifting, in this case, to the left. And then the bit that's just about to leave, just about to be shifted off the end, it comes around and is fed in to the excluded ORs. So just before that bit is shifted off and won't play any more role, it plays one big last role, and then it's the input to all the excluded ORs along the way. Okay. And again, just to show that these things are used, this is a check in the Ethernet frame protocol. Okay. And just again to remind you, the truth table of an excluded, or it was seen in parity. It also plays a big role in addition, so it plays a role in all of these error detection schemes. So if you have the leftmost bit was the one of the inputs to the excluded OR, and then you have some new bit coming into the excluded OR. And if they're both zeros or both ones, we get a zero. If one's a zero and the other's a one, you get a one. Okay. So here I have just picturing it coming in. So originally I had my shifter, and I'm just doing a 4-bit shift to keep it simple and something that I can have on a slideshow. I have some bit string coming in from the right, but moving to the left. And I have a 4-bit shift register, and I have my circles with a plus sign in them. That's my excluded OR. And so that one comes in and it's excluded OR with a zero. So this one here is going to be excluded OR with this zero to produce this one. And this zero just about to be shifted out is excluded OR with this zero to give me this zero. So the leftmost zero and the next leftmost zero were excluded OR to give me that zero. And the zero, the leftmost zero, and the leftmost one coming in from the data were excluded OR to give me this one, that one on the right of the shift register. The middle bits of the shift register are just simple shifts. They don't have the excluded ORs. And then we figure out the excluded OR with the leftmost bit and some one other bit. And so we just keep playing this game. So it was started off 0, 0, 0, 0, then 0, 0, 0, 1, 0, 0, 1, 1. It doesn't really get interesting until we get a 1 over into the leftmost spot, frankly. So that's what changes things. So it's kind of boring in the beginning. You're just shifting. So it's 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 1, 0, 1, 1, 0, 0. That was pretty much just a shift. And now some stuff starts to happen because we're starting off there at that top row with a 1. And so that changed that 1 that was going to come over to that position got changed to a 0 because of the excluded OR. And the 0 that was coming in from the data input got switched to a 1. So we ended up with 0, 0, 0, 1. So now we're back at a 0 in the leftmost bit. And so it's just shifting again. So 0001 became 0010, became 0100, became 1001. Now it's interesting again because there's a 1 in the left-hand spot, 1 in the left-hand spot here, and it is going to flip the 2 bits that come with the excluded ORs. So there was in the top row, that 1 that's going to become the leftmost was a 0, but it got excluded OR with a 1, so it became a 1. And what was coming in was a 0 from the data, and it got excluded OR with a 1, so it became a 1. So we ended up with 1011. And again, we have a 1 in the leftmost bit, so we get some flipping going on. And then we finally ended with 0101. So this is the CRC game. We have data coming in, being shifted, but also some excluded OR. So the data gets modified. And so then the normal error detection scheme, you send your data, you send this result of this operation, you send both the data and the result of the operation over to the receiver. The receiver performs the same operation and checks to see if they get the same answer. Just like in checksum, there's a little trick you can play so that it's easier on the receiver, that they will expect to get sort of all zeros or something. So there's a trick like that. It's a little more difficult to explain, but there is such a trick, and it is what is really done. All right, that's it for CRC. Thank you for your attention.